Okay. Okay, let's start. We're still in this foundation chapter. And today, first of all, I'll first quickly go through some Hong Kong practice that I think you should be aware of. First of all, three important propagations that we use a lot in Hong Kong. And I think at least you should have an idea that when you practice as a geotechnical engineer, you frequently read and come back to these documents when you practice in Hong Kong. The first one, I mean, the one on your left, is basically for private types of projects. So it's under buildings department. And the middle one, or the second and the third one, are more likely for public works projects. And of course, the third one here, when we talk about these marble properties, it applies to generally both public and private projects. There are various ways to evaluate or to estimate the allowable bearing pressures. And you know that allowable bearing pressures will be very important when we are dealing with the ultimate limit states of our shallow foundations as well as our deep foundations. So here summarize a few of them, and I will highlight. First one is what we call the rational design method, and instead of using the term rational, I rather put it like using our first principles, engineering principles. So we start from, for instance, the bearing capacity equations. We start from some other mechanical principles to derive the bearing capacity. And in Hong Kong, we use a lot of presumed values. And these presumed values were actually derived from many decades of experience as well as testing. So we have high confidence that without any site-specific sort of test, we could still use this prescribed value. Of course, you still need to demonstrate that your site conditions fit with the criteria of using these presumed values. So let's go into a little bit more details what presumed values we have. First of all is the vertical bearing pressures. Now we need vertical bearing pressures when we have shallow foundation. We just rest on the soil, rest on the rock. So we could use this vertical bearing. And if we are designing pile foundations, because at the toe of the pile, we still make use of these bearing pressures. So two scenarios, shallow foundation, yes. Even deep foundation, we make use these end bearing pressures. Now you can see that to use these values is pretty straightforward and simple. What you need to do is to understand your material following the descriptions of rock or soil. And these informations in the middle column, these informations is likely read or derived from your logs of the rock, logs of the soil, and you could always ask your geologist helping you to digest, to understand the information, or even as an engineer, you should be able to digest the information from the log. And there are a number of key informations you can see, for instance, is the total core recovery, okay? And now I'm not going into details of all these variables. Probably you have learned in some other courses. And of course, the descriptions of the grade, for example, grade 2, grade 3, grade 4 sort of things. And then we have the UCS, the unconfined compression strength, compressive strength, which is basically one-dimensional compressive strength of the rock. And if you don't have that one-dimensional compressive strength, you can make use of a point loading test to do empirical correlations. So you can see that these descriptions basically describe a few things. First of all, the mass properties or the mass behavior of the materials, TCR, how fractious your materials is, okay? And second of all, it's about the strength of your materials. And in this case, the strength will be described by the UCS, unconfined compressive strength. So once you understand which groups or we call category of your materials are, and you could decide what presumed allowable bearing strength you could use. Okay, it range from, if you have very high quality rock, 10,000 kilopascal, or down to if the rock is, well, okay, not too bad, and 3,000. And of course, for metasedimentary rock and some other types of materials, you have slightly lower values. Okay, normally in Hong Kong, we try our best to find the pile in what we call Cat 1C materials. Okay, so this Cat 1C material will be, normally speaking, we are looking for from the law. So we know at what level we could find this Cat 1C rock, and then we'll drill the pile, and then we'll find the pile there. Okay. And another important highlight is that you see metasedimentary rock. I hope you still remember what is metasedimentary. Okay, it's a sedimentary rock that goes through the metamorphism. And for instance, we have metasedimentary, meta sandstone, meta siltstone. Okay, and you see that here, no matter how strong or how weak your meta sandstone or meta siltstone is, or according to this guideline, we are only allowed to use 3,000 kilopascal. Now, the Hong Kong government, together with some consultants, including AECOM, we are working on these groups of values or this group of materials, because now you see that we only got one category for this metasedimentary rock. Okay, so no matter it's very strong or kind of weak, we are only allowed to use up to 3,000. But indeed, from recent field test, it has been demonstrated that this value could be all the way up to 5,000, 6,000, or 7,000, or even higher. All right. So the plan is to have more subcategories of metasedimentary rock, so that we could enjoy the stronger or better properties of this kind of rock. And for soil, it's pretty straightforward. Okay, basically we use SPTN value helping us to classify how strong the rock is. So the previous slide talks about end bearing or bearing strength, bearing pressures. This table talks about shear, okay, the frictions along the pile. So you can see that it ranged from 150 all the way to 700, depending on the scenario, whether you're in tension, compression, temporary, or transient. Transient means temporary, all right? And in Hong Kong, from time to time, we have these guidance documents. We have these GO publications or BD publications. From time to time, we have revisions. In many cases, we don't actually revise the entire publications, but the government will issue what we call the TGN, Technical Guidance Note, okay, which is used to amend a certain part of the publication. For instance, if we have sufficient data to support that we could use high value instead of 3,000, we could use a higher value. Then one possible ways to do is for the government to issue TGN to amend the practice, so that practicing engineers could make reference to that TGN to use the most or latest, stronger types of materials, values, okay? Instead of going to revise the entire document. So this is a practice in Hong Kong. So in many cases, when you work as a practicing engineers, you always see, okay, with reference to TGN, whatever number, we use this kind of design philosophy or design parameters. Okay, this is what we call TGN. There are other ways to determine those allowable bearing pressures. Remember, I said we could use fundamentals method, first principles. We could use the table well-established values that we use in Hong Kong. Or if you think that my materials are really good and I have a lot of piles in that sort of area, I want to use more aggressive values, then you could use field testing. You could do more work to demonstrate that the value that you propose is valid. Okay, and in many cases, of course, we have to get the permissions from the government, from the buildings departments to accept those proposals. And in many cases, we run a pile loading test to demonstrate that the rock itself, in many cases, rock is got a much higher strength than the value that we put in the existing tables. Okay. So this is one very typical examples of what I call the first principles. We start by using the very famous bearing capacity equations, and you determine the ultimate bearing capacity, and then you apply an appropriate factor of safety to scale down that ultimate values. Right. And once we confirm that the ultimate limit state is okay, we design against the ultimate limit state, and we could move to the serviceability state, okay, which deal with rotations, settlements, or differential settlements. Okay, so here I highlight some of these values that or parameters that you should pay attention to. For example, for instance, in Hong Kong, in many cases we use 25 millimeter as the limit, but in this case, when we talk about total settlements, it's 30 millimeter. Right. Another important thing that I want to highlight is that in Hong Kong, we have established a number of scheduled areas. Okay, scheduled areas are areas that we think involve more complicated situations or constraints that as engineers, when we do the design, we have to take that into considerations. For example, of course, we are focusing on pile foundations, okay? Foundations types of work. So I highlight number 2, number 4 here, because number 2 and number 4 mentions that there are complicated geologies, okay? For instance, we have the meta-sedimentary materials, as well as igneous materials, okay? They have a mix of geological settings. For instance, when you drill a hole, you may encounter granite. And then after 20, 30 meters, you encounter marble. And then you encounter, for example, granite again. So we have more complicated geologies, okay? And I mentioned last week that the problem of having marble is that you may have cavities. It means there's a big hole there. There will be no frictions and to do the frictional support. Apart from schedule area 2 and schedule area 4, let me mention a little bit more. For example, mid-level. The problem of mid-level is that based on the data that we have, mid-level usually have high groundwater table. So slope stability problem or slope stability is always a big concern. And in mid-level, everybody now in Hong Kong understand that it's very congest is a very urbanized, congest area. So whatever work, engineering work that you propose may involve a lot of parties. For instance, even you want to install soil nails, the soil nails may go outside your site boundaries and enter the site boundaries of your neighborhood. So you have to make more considerations of that. Okay. And railway protection area, well, is trivial because whatever work will induce movement or settlement or vibrations. And the railway systems or the trains are very sensitive to vibrations. Okay, so you have to pay extra attention on these movement and vibration things. So what is schedule area number 2 and area number 4? Here shows a simple sort of location plan or map of schedule area number 2, which is in Tin Shui Wai and Yuen Long, the northwestern part of Hong Kong. And schedule area number 4 will be in Ma On Shan. Okay. And then more sort of geotechnical control in these 2 areas. I don't highlight these things, okay? Just want you to understand that these PNET, practical notes for blah, 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 okay, row will explain a little bit more on what sort of geotechnical control should be imposed in these special areas. All right. Now, then I will touch on two subjects here. First of all, when we design a PAL, we construct a PAL, at the end of the day, we want to have some sort of validation check. Okay, so first, before we actually construct the PAL, you may already have some GI information telling you basically what happens in that area. But for PILE, especially in Hong Kong, is special because we always want our PILE to rest or even socket into rock. So you may have a GI record. Let's say I am standing in the PILE locations. Okay, this is where I want to drill or construct my PILE. Before the construction, I may already have GI information. Let's say 200 meters away, 200 meters to the north, and maybe 50 meters to the south, somewhere, all right, around this area. So I have some basic understanding of where I should expect my rock head in these locations. But in many cases, the rock head varies a lot. So in order to have more precise information to do the drilling, to do the quality control, we have what we call the pre-drilling at the locations where you're going to put your PAL. And once you have your pre-drilling, you know exactly what's going to happen in at least, well, you got a 1 meter PAL. You may argue, I got 1 meter PAL. If I do a drill hole, probably just 100 millimeter. Would it be representative sufficiently? Well, better than nothing, I would say. So at least you will have more information on what sort of where your rock head should be, and you may be able to get more samples to do laboratory tests if you want. Okay, you would get the rock samples so that you could run UCS. You could get a UCS value so that you could put whether your rock is under Cat 1-2, Cat 1B, Cat 1C, sort of things. Okay, so this is pre-drilling, and the number of pre-drills depends on the size of the pile, and also depends on what government or what client you're working with. I understand that in Hong Kong, I can't remember, probably housing or HSD, I can't recall. But for a large diameter pile, up to 3 drill holes, you have to do within the footprint of your pile. Okay, but normally speaking, you need at least one. Okay, that's for bore piles. Bore piles. Okay, for driven edge pile, you don't need to do that, but you have to do it in grid system. I remember every 5 meter. Yeah, that's a I could put it here. Every 5 meter, you have to do a pre-drill. Okay, so you have more information to tell you where you should expect your rock head. So this is pre-constructions. And post-constructions of your bore piles, you also need to do some tests to verify or to demonstrate the quality of your pile. So here I highlight a number of things. First of all, is the interface proof drilling. So you have to drill through the interface between your pile, concrete basically, and the underlying rock. So this interface pre-drilling will help you to understand whether the interface is clean. Why we need a clean interface? Because if your interface is not clean, that means during the construction, concreting, drilling, you got a layer of sandy, silty, clayey, whatever materials there. When that layer is subject to loading, it will be compressed. So you see additional settlement of the pile because now you have a soft toe at the pile base, right? Because your pile is not actually directly resting on the rock, but it's resting on the fill, on a layer of filling materials. Okay. So this is the interface core will be used to prove that the workmanship is okay. And there are some other tasks which are used to demonstrate the quality of the concrete. For instance, there will be no honeycomb. There will be no gaps that you didn't actually fill with concrete, something like that. All right. And of course, you could also do some sonic test. Normally speaking, sonic test will be due before you pound the concrete. You want to know the shape of the pile. Okay, you send sonic waves. So these are a little bit more details, and I better skip. How about torrents? People actually not pay too much attention on torrents, but because they think in a way that I design a vertical pile, so the pile must be vertical in the field. Well, this is definitely not the case, right? You draw a vertical pile. It doesn't mean that in the field, your pile is really vertical into the ground. So we have some sort of acceptance criteria. Okay. Now, looking at this number, you may not have too much feeling, but let me put it this way. What do you mean with 1 in 100? I'm talking about this verticality, which means if you are drilling a 100-meter borehole into the ground, okay, 100 meter in the ground, you are only allowed to, at the pile toe, offset by 1 meter. Don't think this is easy. It is not easy indeed, right? You're having a very slender sort of column, and then you drill, you put in your casing. There could be lots of problem, lots of scenarios that your piles actually deviate from the vertical directions. Okay, so we need to impose some criteria to check it. Just like what? Just like tunnel boring. Okay, you think, okay, I have my tunnel boring machine TBM. This is the launching shaft, and that's the retrieval shaft. So I think, okay, this must be a straight line, go all the way, and then to the destinations. This is not the case because when you do the drilling, your machine is heavy, so you gotta sink into the ground because your TBM machine is heavy itself, right? And if the ground is not strong enough, it tends to sink, and it tends to tilt laterally as well. Okay, so there will be a lot of adjustment during the course of drilling. There will be a lot of control, lots of ways to realign your tunnel boring machines. And of course, this is out of the scope today. Okay, so that's it for the power foundations. Let me quickly summarize what has been taught in this power foundation chapter. First of all, we spent quite some time to derive a formula, a complicated formula, I have to put it this way, to determine the capacity and settlement of one single pile, subject to vertical loading. Okay, and the key there is not the equation itself, but I want you to understand how, based on first principles, these kinds of equations could be derived. Okay, and of course, if I give you that equation, I expect you to know how to make use of that equations to do some basic calculations. This is my expectations. Second, we spend some time to talk about that lateral resistance. Of course, definitely on very simple case that either clady materials, SU materials, or C5 materials, sandy materials. And we have different cases like long pile, short pile, and that means different combinations. All right. Again, the important concept is derive the equation based on first principle. For example, you see that we basically draw the free body diagram. We do moment equilibrium, force equilibrium, basically the basic stuff that we learned during first, second years of our undergraduate study. And derive equations. And if I give you the equations, you should be able to make use of the equations to do the calculations. Okay. And I've also showed you some design chart, simple design chart, just a number of charts that help to estimate movement, lateral movement of the pile, bending moment of the pile, shear force of the pile. So I have in-class exercise on that part. So make sure you know how to do it. Okay, I'm giving you some hints for the coming midterms. Okay, so pay attention. And then I quickly go through some basic things or some important concept that I think as a practicing engineers in Hong Kong should know. For example, what sort of guidelines that we are using in Hong Kong and some other basic things. All right. So that concludes the power foundation part. Any questions? If not, let's move to a new chapter. And before I move to a new chapter, I think you have received these announcements, right? I think everybody received those announcements. Okay, so we have confirmed the midterm on March 27th, so 1.5 months later. All right, and likely before that, I will, well before that, I will upload the equation sheet that you're going to use in this midterm. All right, so you know what sort of equations will be provided. And I will also upload the first assessment assignments. Okay, I still trying to figure out how I upload these assessments, the assignments onto. I think, am I correct that I just upload here in the learning portal and then you submit through the portals, right? Okay, good. Okay, then let's move to new chapter. It's on slope stabilities. Now, last week I did ask, okay, how much basic understanding you have for slope stabilities, and some mentioned that okay, basic things like circular slip, method of slice, Jambu sort of things has been mentioned. But then I received some emails saying that okay, still a good idea to review quickly review some of these basic concepts. So I think I'll quickly review some basic concepts that I think will be important for the slope stability part. It won't take too long, but I hope it could refresh your memories. So that's what I'm saying. The introduction part as well as the total stress approach. and then move to effective stress, and then talk about translations. Have you learned about these translation slips? Infinite slope. Yes, right? Some say yes. Some no response. Probably you forget. Anyway, I'll quickly touch on that, and then some more on method slides, and then two probably new concepts to you will be how we use nails to stabilize a slope, and other important concepts that we or scenarios or situations that we face in Hong Kong is loose field slopes. Okay, and probably this is the, I would not say only chance, but this is a rare chance that you will be exposed to in a formal lecture manners on what do you mean by loose field and why loose field will be important. I won't go into details of the design because there are guidance documents that teach you how to do the design, but I'll touch more on the basics behind the fundamentals, the salt behavior, and why or what do you mean by loose field, and that's important, especially when you work as an engineer. In many cases in Hong Kong, you have to deal with slopes. I don't think you can avoid slope problems in Hong Kong as a geotechnical engineers. And if you have typical cut slopes, you use saw nails to do the reinforcement, simple, straightforward, no problem at all. But when you face the situations of loose field slopes, the design philosophy, the failure mechanism will be quite different from a cut slope. And when you encounter that, you do your design, and when you do your chartership assessments, normally you will encounter assessors from geotechnical engineering office, for instance, or even somebody who has experience of slope engineering, and they may like to ask you loose field slope things. Okay, so I think it's important to understand that. So start with introductions. I like to ask questions why or what's the causes of slope instability. Okay, why slope will sort of fail. But before fail, actually, let's look at something more sort of minor, is what we call erosions. So what does mean by erosion? Erosion is simply a washout. Okay, so you may have rain and they just keep washing out. It's nothing related to groundwater pressures or so pore water pressures of the soil. It's just a washing process. So basically, it's rainwater. You just wash out the surface layer of loosened soil. That's it. Okay. Of course, by having this minor washout, you change the geometry of your slope. And because you change the geometry of the slopes, the entire free body diagram will be slightly changed as well. And because of that, it may also trigger a more or larger scale landslides. Okay, so even you start with a minor washout, it implies some other things. Okay, second is rainfall. Rainfall definitely is the main reasons causing slope instability, especially when we say rainfall, we put in the categories of seepage. Okay, that means there are water pressures or water flowing in your slopes, inside your slope, and causing pressures. And here I put into two different categories. The first one is what we call the shallow failure. Shallow failure normally refers to the first few meters of rather the first few meters of failure in the field materials, and is caused by what we call the buildup of perch water table. Now, perch water table is developed because you got rainwater infiltrate into the ground, and you could think maybe I draw something here to help you to understand what happened. Let's say this is a slope, you got a layer of, let's say, fill. And let's say I have some CDG, make it very straightforward and simple. Okay. And of course, it can be not fill, it can be colluvium. So the key message is I have a rather loose materials, more permeable. The key is more permeable materials. And then I have a layer of material which is less permeable. So the permeability here, let's say K1, this is K2, and K1 is larger or even much larger than K2. Okay, let's say the slope is completely dry, at least up to this layer. All right, maybe we have, this is, let's say this is granite. Okay, this rock. Maybe the groundwater is extremely low, let's say here. Okay, so basically at the interface, at the surface of the rock layer. Now you got rainfall coming. All right, so rainwater will infiltrate into the soils, right? Because it's natural because of gravitational force. And so rainwater will flow, seep inside the loose fill layer. Now it encounter another layer, CDG, which is less permeable. So what's going to happen? Water will build up here. So we will build up what we call a purge water table. This is still dry. CDG is still dry. Okay. But you got a water table developed here. This is what we call the purge water table. It's not the main water table. Main water table is still here. Okay. So you develop a purge water table and probably just keep going, keep rising and rising. And basic soil mechanics tells that if you got portal pressures, your effective stress will drop. If your effective stress drops, your shear strength reduced. And maybe up to a certain point that your strength is no longer larger than your stress, shear stress, you got failure. So this is why we have shallow failure due to rainfall, development of purge water. Okay. This is not the end of the story. Let's say I'm in a huge catchment and definitely there are more soils upslopes, right? So even at the very beginning, your water somehow got stuck here and developed the purge water, but it could still seep into the CDG because CDG in this case even is less permeable. It doesn't mean that it is impermeable. It's still permeable. It takes time. Okay. So with gravity, the water will still go into CDG. That means here the groundwater, the main groundwater will still rise because you got water flowing from upslopes. So your main water will rise based on this seepage from the upslopes. If your main water rises a certain level, again, same scenario, your shear strength will drop. You may have a deep failure. So we have two things here. First is what we call shallow failure, possibly due to the development of purge water. And then second scenarios or subsequently, we may have deep failure due to the development of the main water table. Okay. Now here I'm highlighting two scenarios. It doesn't mean that it will definitely happen. No. If the ground is gentle, it won't happen, right? If your material's strength is high, it won't happen. Okay, so it only tells that, okay, that could be a possible mechanisms of failure. It doesn't mean that it will always happen. Okay, right? Then earthquake. Similar to the seepage problem, earthquake could generate slope failure, at least from two different perspectives. First one, you got earthquake, that means you have seismic loading, quick shaking, and even sand, you got like very high permeability, pore pressure, excess pore pressures could still build up, right? Because you're gonna have a quick loading. So in that case, you generate the excess pore pressures. And again, excess pore pressures, sandy materials, you have liquefactions. Okay, this is really a seismic types of liquefactions. Your sand behave like fluid. And I believe that you might have that sort of model box. Have you seen this kind of model box that the sand turns into liquid? Have you seen that before? No? Yes? No. Let me see. Later, after break, let me see if you could take out some YouTube video showing you. It's interesting. It's quite fun, and well, let me tell stories. Okay. After that. Okay. When I finish this one. Okay. And second sort of mechanism is that you have shaking. That means you are imposing a lateral load on your materials. So now you have additional load. You may trigger a landslide as well. Okay, I will have some free body diagram to illustrate the second concepts. Now back to the first one, the seismic things, the liquefaction things. Well, in Hong Kong, because normally speaking, we don't have earthquake, so we didn't pay too much attention to that. When I was working in New Zealand, because New Zealand basically we have earthquake every single day. And so seismic, or as a geotechnical engineer, seismic will be a very important subjects. So we used to have, during open day, we used to have you may consider like a fish tank or something, all right? We put loose sand there, and then we put some Lego block or whatever buildings on top of it. It's fully saturated, and we induce shaking to that. And the shaking could be easily done by, you could using something to ham it, or you use a shake table, but we use a simple way. We just use hands to tam it. All right. We normally ask the visitors to ham it. And then this kind of additional quick loading, you just ham it, will induce like seismic loading. And you could quickly see that your saturated sand behave like liquid. So entire Lego block just sink into the ground, because the laws or the shear strength, from saw mechanics perspective, it is very simple. Let me quickly write the equations. Your shear strength can be described by Mohr Coulomb failure criteria, right? C dash plus total stress minus portal pressures tangent phi. Right? This is your shear strength. Sandy materials, no cohesions. When you apply seismic loading, your portal pressure will increase. If you increase all the way up to close to sigma, this term will go to 0, right? So even your tangent fine is okay, right? Tangent 35, tangent 40, it really doesn't matter, because your effective stress has already turned to 0. So the strength goes to 0. Okay. A material with shear strength equal 0, water doesn't have shear strength. So it behaves like water, right? So you turn your saturated sand into water, right? And that's why saturation is important. You could pick up what I keep mentioning is I got a fish tank, sand filled with water or saturated sand, because we need water to build up the pore pressures. If there's no pore water, no matter how you hand it, you won't have any change in this term. There's no U or delta U, right? It's dry, okay? So that's the, from a geotechnical soil mechanics perspective, why when the sand liquefied, it lost all the shear strength. It's because of that McCollum failure criteria, as simple as that. Okay. And then the last three reasons will be pretty straightforward. Well, everybody could expect this kind of behavior. When you apply loading, external load, for example, you build a building at the crest, well, you increase the loading, well, definitely you may induce failure. Or if you dig a hole, if you make an excavation, you excavate some soil, you excavate some, let me draw something like this. For example, you got a very gentle slope, okay, no problem at all. But if you dig a big hole here, okay, I got a construction, I just excavate this soil out. So you got a very steep slope here, okay? You lost the support from these chunks of soil. Excavation could induce slope failure, okay? Last one, again, straightforward. If you have a, let's say I have another slope here, you got some thin layer of very weak materials, okay? So, and then the orientations of those weak material is having a daylight here, okay, which means it hit your sloping face. So it's easy to have failure because this part of the material have a much lower strength. So it's easy to have a failure like that. All right. Okay. Any questions on these things? Calculation is one thing, but I think to understand the concept is even more important. Calculation is not complicated at all for slope part. Right. So this is just a quick summary of what are types or typical types of slope failure. Of course, if you talk to experts, slope engineering experts, and I once talked to one of the professors, he said, well, there are 30 something or 20 something types of slope failure. And well, here we just quickly summarize into a few of them. Because why they have so many types? Because they further develop, for example, translational slip into different branches. Okay, for example, in Hong Kong, doublet flow is another kinds of slope instabilities. Okay, and in this course, when we look at the calculations of factor of safety, or when we do the calculations of slope stability or instability, we'll focus on circular, non-circular, and translational. Compound, to me, is basically the same as non-circular. Right? Same thing, same philosophy, could do the calculations. Remember, we have the method of slice. We just chop it into vertical slices. All right. We do it one by one. Before we move into detailed calculations, let's look at what strategies we have for the design calculations. We use what we call a limit equilibrium method. What do you mean by limit equilibrium? In simple word, to me, is we draw free body diagram. We consider force equilibrium, moment equilibrium. That's it. right? Limit equilibrium approach. And we apply a global factor of safety. We just apply one factor of safety to the entire scenarios, okay? We use a factor of safety to reduce the strength. That's exactly what happened, okay? So, put in the details, what we do with a slope, assume you have all the information that you need. You have the shear strength, C dash, fine dash, or SU, gamma, water table, and tension crack, all sort of informations you have, right? What we do first is to assume a failure plane, okay? So for example, in this case, I assume trial phase 1 is a potential failure. And what I do next is to draw the free body diagram for this trial's volume or trial mass 1. And then we consider force equilibrium and moment equilibrium, step number 3. And then based on that force moment equilibrium, I could calculate FOS. Okay. And then I repeat, we go back to step number 1. I pick another trial. Okay? And then repeat it again until we find the so-called minimum FOS, which means the failure plane that give us the minimum factor of safety until we find that. You ask, I hope you ask the questions like, how do I know that this is the minimum? Okay, how to demonstrate? For example, when we do a submissions to GO, how can I convince the checking engineers that this is already the minimum? Okay, we have several ways to do, and one way that we adopt is what we call the converge method. Converge method, put in a simple word, is that I have 3 pairs of slip planes, okay, closely packed, okay, similar geometries. And then I found that, for example, in this case, if they are very closely packed, and trial phase number 2 is the minimum among these 3. So this is the minimum one for this set. Okay. And then I may have another set. Let's say, whoa, a very deep failure. I got similar things. And then I compare patches to patches, batches to batches. Okay. And of course, with our experience in Hong Kong, we understand that most of the time in Hong Kong scenarios, these very deep seated failure will not control, normally speaking, will not control. Okay. So with more experience, basically you could tell once you're given a simplified slope geometries, you easily identify where would be the critical failure slips, okay, or somewhere around, and then you could do the calculations quickly, right? And of course, you don't do hand calculations. You use most of the time in Hong Kong we use slope W to do it. Okay. Let's take a break, okay, before we move to this short and long-term stability. Let's take a short break. Let's come back 7:40. All right, about 10 minutes break. Okay, let's resume. When we do the stability analysis, remember we have to do using the limit equilibrium approach. We draw the free body diagram, and then we do force equilibrium, moment equilibrium, which means we need to have the strength of the materials. Otherwise, we cannot draw the free body diagram. So we have two different approach, basically the total stress approach or the effective stress approach. When we say the total stress approach, it will be used to describe the so-called short-term stability scenario. And during this short-term scenario, as I mentioned, short-term, from the name itself, you see that the portal pressure will not have sufficient time to be, the excess portal pressure will not have sufficient time to be dissipated. Let me So we use the total stress and the undrained shear strength to do it. On the other hand, if your material basically is sandy and the permeability is high, we use the effective stress approach together with portal pressures. Okay, we consider the change in portal pressures. And when you want to estimate the portal pressure, in many cases, we have to draw the flow net in order to evaluate the portal pressure. Later on, I have examples to demonstrate what do you mean by flow net in this scenario, in this context. Factor of safety is an important concept when we do limit equilibrium, because what we want to know at the end of the day is the FOS value. Okay. Now, FOS, we have many ways to determine or to define an FOS, but generally speaking, we use force to do it. And when we say force, it will be the resistance in terms of force over the driving one. And by the same token, which means is the mobilized shear strength over the shear stress. Okay. And of course, we could define FOS using moment. And next slides, I have examples to demonstrate how we use moment to define FOS. Basically, same thing, all right? It'll be the resistance over the driving force. In terms of moment, that will be the restoring moment over the disturbing moment. So let's start with several scenarios. Okay, I'd like to start with something simple and easy to be understood, which is something that we studied during high school, right? Quite some years back. It's about frictions. So if you are dealing with a purely frictional materials, no cohesion at all, just frictional. It looks like what? It looks like you put a block over or on the table, which is something that we learned in high school physics, right? And you push it, it will generate what we call friction, resistant friction, which oppose the directions that you impose. And if you could recall these simple equations in which your frictions equals to a coefficient of frictions multiplied by the weight. If you take a look, actually, if you expand this, it looks like what? It looks like your frictions, that means your shear, I still put mu here, which is a coefficient. Weight is something like what? Your normal stress, right? And you find it very familiar to you because in solid mechanics term, instead of using mu, the frictional coefficients, we call it tangent line, right? So basically the same thing. And indeed, we learned some basic solid mechanics during high school, right? That's the frictional coefficients. Just a different ways to present the same concepts, right? So to achieve to achieve force equilibrium, and if in this case you don't have any movement, your applied force will be balanced by a friction with the same magnitude but opposite directions. So we define the FOS like this, okay, which is your resistance over the F. This F, small f, is actually the maximum resistance that could be provided by your weight. Let's add one more term. So in the previous slide, it's purely frictional. So we use a sliding block to represent it. Here, we add a so-called cohesive term. And in solid mechanics, that's C dash. So the rest will be pretty straightforward, right? You have your friction, you have your frictions, you have your shear stress, and then the ratios will be FOS. This is an other concept that some researchers, let me put it this way, like to or they like to use this concept to this way to understand what happens. Let me try to explain a little bit. So the red one represent the strength, the ultimate strength. Okay. And this is a simple Mohr circle, right? So if you have a pair of stress which form the green one, so if I have my sigma 3, sigma 1, I have my sigma 3, I will form the green Mohr circle. And this green Mohr circle has not touched the failure envelope yet. So we know no failure at all, right? And then people like to use the concept because we have friction angle. So they want to put everything in the context of friction angle. Instead of comparing the strength, they compare the friction angle. So that's why they invent a parameters called the mobilized friction angle. So in this case, now your current stress or stress state form the green Mohr circle. And if you use the same Mohr Coulomb sort of analysis approach, this green Mohr circle will touch a virtual failure envelope, the green dash one. And with this green dash failure envelope, you have a angle, and I denote it by phi mobilized. And of course, in this case, your phi mobilized is definitely smaller than the friction angle of the soil. So no failure at all, right? So basically the same concept, but instead of comparing the strength, they compare the friction angle. They call it the mobilized friction angle, and really the ultimate or the strength kinds of friction angle, okay, or angle of internal frictions. This is something that looks simple because whenever we ask about this shear strength, we'll say, oh, Mohr Coulomb failure criteria, right? Tau F equals C dash plus something. And we keep saying that if this is undrained, my friction angle turns to 0. And I have emphasized many times that undrained will not turn your friction angle to 0. Undrained conditions will only turn your phi u to 0, not the friction angle. Friction angle is always the friction angle, right? It won't change the properties of your angularity and your pegging, okay? But why? During undrained conditions, we could say phi. So when it's undrained, why we always say, oh, we put phi equals 0? Why? The reason is think about programming. Think about programming. If you write a program, you have to denote the strength of the soil. So you will write something like strength equals to C plus sigma dash, let me make it simple, tangent phi. Okay, that's the Mohr-Coulomb-Fayet criteria that we always use. Or maybe I expand it a little bit. So it's C dash times sigma normal minus pore pressures tangent phi. Okay. This is the equations that were built in programs, slope W, let's say. Okay. If we are running a string analysis, everything looks perfect because we just plug in our C dash, we just plug in our phi dash, we know effective stress, we know total stress, we know pore pressures. So it works, the entire equations. We know the shear strength of the soil. But what if this is an undrained case? If this is an undrained case, what we do? In slope W analysis, if this is undrained clay, for example, we think it's an undrained case, we will not use fraction of 30 or whatever. We put it like 0. And instead of C, we don't put C. We replace this C with what? Undrained shear strength, SU, right? Or someone would like to use CU. Same thing, just different symbols. Okay? Because now I'm running an undrained analysis. So you know that you plug in a different values. You do not plug in C equals to 5 kilopascal or 0 kilopascal in the drain case that you use in the drain case. But instead, now I'm dealing with clayey materials. I do not put C dash. I will put undrained shear strength to replace it. If you put these combinations into the equations, you will find that your shear strength will becomes what? SU. Right? That means you put in some sort of incorrect number. You put an incorrect friction angle because you want to turn this term to 0. You want to turn it into 0 because you do not know how much pore pressure will be generated. This is undrained case. Pore pressure will change. And by doing this, you don't care what happened to your sigma n and sigma u and u. You don't care because you don't care this term. Because this entire second term will be cancelled, right? You plug in phi equals 0, tangent phi 0 as well. Okay, so you purposely neglect this term. And you replace the entire strength directly with SU. SU is something that you find from laboratory tests. Right? You don't need to puzzle what will be effective stress, what will be total stress. And that's exactly why when we do the total stress approach, you do not need to vary how much pore pressure has been developed. You don't need that term. You don't need second term, right? Okay. So this is the first things why we plug phi u equals 0. Someone think in a different ways. They will argue saying that, oh, it's because if I run a UU test, what happened in a UU test? People keep saying that, okay, I will have two same size small circle, right? So I fit a line, and in this case, the so-called tangent, the so-called friction angle will be 0 because it's horizontal line. Similar idea. Why? Because you're using the same equations, which is a linear equation, just like linear equations, right? With slope and intercept. So in this context, you have a slope, which is 0, and you have an intercept. And in this case, your intercept is as u. Same thing, right? In this context, you may assume, well, they are actually the same. From curve fitting perspective, yes. But if we want to take a deeper look into what happened, and this is something that I want you to think about it. Why we keep saying that doing a UU test will give you identical Mohr circle. Why? Is it always the case? The question is it always the case? Let me try use, I try to get a blank page. Okay, let's say here, I use a blank page to draw something. If this is a ground, let's say this is clayey materials, okay, and that ground is clayey materials. Let's say normally consolidated clay. Okay. I take a samples here. Let me call it A. I take a sample also at the same depth, B. Okay. I take out 2 samples from the ground, assuming no disturbance, same conditions, everything the same, including their microstructures, including their stress history, identical, they're twins, okay? Sample A, I bring it to the lab. I apply pressures in the vertical directions. I shear it, right? What will I get? I will have a Mohr circle developing like this because my sigma 3 is 0. Keep growing until fail. This is the UU test results of specimen A. Okay. Now I have specimen B. This is A. I got B. Twins, identical. But instead of just shearing under low confinement, 0 confinement, I bring it to, let's say, 50. 50. So isotropically apply 50 kilopascal. This is a UU test. I didn't turn on the drainage valve. No water is allowed to flow. Just apply the loading. So what's going to happen to the effective stress? No change. Effective stress doesn't change, right? Pore pressure would take up all the excessive sort of confining stress. Assume definitely this is fully saturated. Okay. Effective stress doesn't change. A, B, 2 specimen. Before you apply this confinement, they are twins, identical. Now, specimen B, you apply 50 kilopascal to it. Effective stress doesn't change at all. They are still twins, right? You haven't changed, you haven't modified any properties. You haven't densified anything. You haven't changed any void ratios. You haven't changed any microstructures. If that's the case, B, let's say this is 50 kilopascal, initial point. You run a UU test. So you apply vertical stress on top of that 50, it grows bigger and bigger, right? Same thing. When will it fail? They are twins. They should have the same strength. That's the only reasons why we draw something like this. Because we are making a very important assumptions that before the test, before the unring test, actually they are twins. Actually, they have the same strength. And what we did to them is we bring them to a different initial state in terms of total stress, but effective stress, in terms of effective stress, there's no difference. Okay? So be very careful. That's the only reasons why we say these two specimens will have the same SU blah blah thing. It doesn't mean that UU test will always give you this curve. Why? If I take out a specimen C here, specimen C locate deeper into the ground, so I would believe that because it's normally consolidated, so I would believe that specimen C must be denser as compared to A and B. If specimen C is denser, more closely packed, the strength should be stronger, right? Very clear, right? It's packed closer. So if I bring specimen C to the lab, I use a different color for better illustrations. So specimen C, I bring to lab. So C, again, no confining pressures, but I will apply vertical directoric shearing. So C here at the very beginning, I shear it, so bigger and bigger. It will not stop at the same size. Why? Because it's stronger. So I expect to see a larger unring shear strength, right? So in this case, the UU results of A and then the UU results or the SU value of C will not be identical. If you have these two more circle, you won't get a horizontal line. Okay. Now, it may look trivial to you, but what if I do similar things, okay, same level as C, I got a D specimen. So this is my D specimen. And instead of having 0, let's say I put 100. 100. Okay. And I share it. Now C and D are twins. So if I do it this way, I start at 100. So I will expect to see a more circle with the same size as C. Okay. It looks fine. Looks like, well, we are doing something understandable. But if, of course, now we do it step by step. If someone compare A and C, A and D, A starts here. Go back to this. A starts here. Maybe I put it there. A starts here. Okay, A fails at here, which is the size of this one. Let's say this is what we call SUA. Okay, so this is SUA. And then I put my SUD here. This is 100. So I start the test and I run bigger and bigger. Let's say I fail here. SUD is bigger. Okay. Now you have two different size Mohr circle, failure Mohr circle. If you didn't pay attention to that, you would say, whoa, I got two Mohr circle, failure envelope. I got C dash, I got fine dash. Fine dash is not 0. Totally incorrect. Why? They are total stress Mohr circle, right? These effective stress principles will give you the Mohr Coulomb failure criteria. They are on effective stress. You should never use total stress to do it. first mistakes. Second, people say, oh, I know, Ryan, I know they are total stress. So I won't do something like this. I know it must be a horizontal line because UU test, of course, is incorrect, right? I know, well, I shouldn't have a gradient like this. So I will fit the data with something like this. Okay, I take the mean. Okay. Yes or no? Correct or incorrect? Strictly speaking, incorrect, right? Because this is never the strength of A, never the strength of D, but it's somehow the mean strength of A and D. So it means what? It means that instead of characterizing your ground with a, let's say this is my undrained shear strength with depth, instead of having an increased undrained shear strength with depth, because from A to C or B to D, you should expect an increase in undrained shear strength, right? It's normally considered clay. The clay becomes denser, so stronger. Now you use an average approach. You got something like this. I cannot say you are incorrect. You are using an average approach to characterize your ground. Okay. Technically, I can't say that. But if you don't understand that you are making an average, then it will be problematic. So you should know what exactly you're working on. All right. And of course, from time to time, we have to make assumptions. We have to do the averaging. Now, why I have to mention something like this? Because it does have practical implications. When we, let's say in a reclamation types of projects, we retrieve a lot of samples from the ground. And I know this is what? I know this is clayey specimen. I will run UU test. So I collect lots of specimens from different depths. I run UU test. I should not put everything into one single figures and take an average. I should not do that because they are different depth. They should have different strength. Instead, what I would do is I would take individual failure envelope. I get the SU. I get the undrained shear strength for individual test results. I put them back in the corresponding depth. Let's say this is the undrained shear strength for A. This is undrained shear strength for C level. And if I have more level of test, I will have more test results, right? At different depth, different value. Then I will try to find a maybe straight line, maybe curve, whatever you like, to capture all these data points. That will be a better way to characterize the ground instead of putting all the results together, right? Okay. This is the way we analyze the results. Questions? Questions? Okay. Just like what? Just like running Traxel test. You run one Traxel test, not to mention multi-stage. Okay, you run one Traxel test. You got C dash and phi dash. Okay. You run another Traxel test, same soil. You got C dash and phi dash. How would you analyze the results? You will not get friction angle 1 plus friction angle 2 divided by 2 and take the average. You won't do that, right? Instead, in that case, you put everything into one single Mohr circle sort of plot and get an average results for that C dash and phi dash. Okay, and you see that that's different from what we're doing here. So for different types of results, for different types of scenario, we use different ways to do the analysis to get the C dash phi dash. It's not as trivial as people may think. Okay. Now, why I have to spend so much time on shear strength? Because the rest are simple math, force equilibrium, moment equilibrium. We play around with the mathematical tricks, okay? But this is really soil mechanics. And soil mechanics actually dictate whether you success or not in these professions. All right. Start to review the basic FOS thing for circular failure in undrained materials. Find U equals 0 materials. Okay, SU materials. I think you have been taught on these things. So I don't think I need to explain too much. It's simply moment equilibrium, right? We consider total stress, and then you have the weight of your moving mass, W, and then you take moment arm sort of things. Okay, you write these equations. And we often say this is the so-called Swedish circle method. It's the easiest one. Okay, equilibrium. Of course, we have limitations. Can you name the limitations for this? Any limitations for applying this formula to do the FOS? Yeah, we don't know the portal pressures, right? But let's say, assume it's okay. Oh, I know undrained shear strength anyway. So short term, I don't need to care about the portal pressures. Right? We're making assumptions in this case. First, circular, right? It's circular. Okay. Second, only one SU is used in this case, right? So if I have multiple layer at different depth, let's say at different depth, I have different SU, which, well, in many cases, yes, right? There's not a single value. It changes with depth. We cannot apply these equations. Of course, you could still argue, okay, then let's take SU average to do it. Yes, you can. Estimations, all right? And of course, you could move your circular art. For example, this is a circular art that we use here. I could move my circular art, let's say here, okay, or different locations. Then I will have maybe different radius, or maybe even the same radius, but different theta, right? So I have a different FOS, okay? But the key here is if your critical slip plane is not circular, you will not able to find that because you're making assumptions that is circular. No matter how you move your failure envelope, it's still circular. But this is a good starting point, we'll say. Let's make life a little bit more complicated. What if, apart from W itself, apart from the dead weight of the material itself, assume I have a building on the slope crest, which gives us a light load of FL. So we consider that. Again, moment force equilibrium. What if I have a crack at the crest? And the crack is filled with water. That means we have water pressures acting on the face of the crack. We take that into considerations as well. So by moment equilibrium, you get these new FOS equations. Now, forget about how it is derived, its basic force equilibrium things. Let's take a look at the equation itself. This is something that I always do, whether it makes sense or not. If I don't have any force at the crest, if I don't have any portal pressure in the tension crack, these two terms gone. It go back to the original Swedish formula. That's okay. If I have F at the crest, I put in the denominator. What happened to FOS? Increase or decrease? If I got a FL, XL, FOS will be reduced, right? By keeping other things otherwise the same. That makes sense, right? Because I adding some load at the crest, so my FOS should be reduced. Similar things happen to your force water, right? It push your potential failure mass downward, so it makes sense, right? And this is a critical step. Why I have to mention that? No matter how you derive equations, at the end of the day, you take a look at the equations to see whether it makes sense or not. This is a simple but important critical check, whatever equations that you derive. And this slide simply shows you what happened when we say it's a crack filled with water. So this little crack will be all filled with water. So you have a resultant force from the triangular water envelope, right? And those basic, I think you could you should be understood from your retaining wall calculations or something similar. And this is equations that how we derive the depth of the tension crack. I think I mentioned this last lecture as well. Right? So we just think, well, this is tension crack, so low lateral pressures, and we have this failure envelope, right? Okay. Stay with the undrained shear strength. Stay with the undrained approach. A professor called Taylor, which is actually a very famous professor in soil mechanics after Tasaki. Everybody knows Tasaki, but indeed Taylor was a famous one. Unfortunately, he died young. Otherwise, people think he would be as influential as Tasaki. So he proposed a chart like this to evaluate FOS, of course, in a very simple scenarios. So we have a thick layer of clay with a geometry described by the upper part of these slides. And he suggests that the factor of safety or the maximum or minimum factor of safety of this slope depends on the undrained shear strength, depends on the height, unit weight, and the number called NS, stability number. Let's take a look first. If SU increase, F increase, it makes sense, right? Your undrained shear strength increase, factor of safety increase. Your height increase, slope height increase, less safe, makes sense. Material becomes heavier, less safe, also makes sense. Okay, so the missing part is NS. How to get NS? Let's use examples to do. Oh, what happens here? Whoops. Wait, what happens? Oh, forget about what? What happened to this one? Something wrong with this one. Let's see how I can, if I can fix it. Just copy this one here. Okay. All right. Illustrative examples. 45-degree slope. Clay, saturated clay, unit weight 19, 8 meter tall, and undrained shear strength 30. Okay. So let's take a look at the keywords here. I asked you to use the chart to determine the minimum FOS. Slope degree 45. Okay, so beta 45 degree. Simple. Deep layer of saturated clay. What does it mean? Deep layer. D will be infinite, right? Because we say it's a deep layer. So D must be extremely large. So D infinite. These are the D number. 1.0, 1.2, 1.52, 4, infinite. This horizontal line, infinite. Okay. So we use a chart, rewrite it. 45 degree, we draw a vertical line all the way. It touch that's infinite one. D equals to infinite, and then we read the number 0.18. So this is 0.18. Read the number, plug back into the formula. We find minimum FOS 1.1. Done. Okay. One more example. Instead of a deep layer of saturated clay, let's say we found a firm bedrock 10 meters below slope crest. What does it mean? It means that this is 10 and the height is 8, right? So you could work out D value because the questions tell us that from the crest to the bedrock is 10 meters. Okay, so work out, in this case, your D will be 1.2. Same approach, 45 degree, go up all the way, it touch a D value of 1.2, so it's this curve, and then we rate it 0.17 around, so we plug in, oh, FOS slightly improved. Okay. Then if you are smart enough, you see that if I have a slope angle greater than 53 degrees, everything merged to one single curve. Yes. So if your slope is 60 degrees, let's say here, if your slope is 60 degrees, you don't need to vary where you find that firm layer. Why? Why? For very steep slope, which is larger than 53 degrees in this case, that's what Taylor proposed. You don't need to worry about the presence of this firm layer. Why? Because the slope is so steep that failure will likely happen in this region, right? So it will dictate by the slope angle itself. You won't have a deep seat failure like this anyway, because the slope is so steep. Also, if I could draw, here, the slope is so steep that failure will happen here anyway, right? You don't need to worry whether you have a firm layer or not. It happens in the slope body itself, right? Okay, so that's the reasons why everything merged back to one. Of course, I didn't have the original publications. I think it's published in 1940 something. Okay, well before I was born. I don't think I'll go back and read those papers. I don't know how it derived 53 as the limit points, and everything looks so sudden. The change looks so sudden. I don't really understand why. Anyway. Okay, so that's the Taylor chart. One more example before we take a break. Remember, we have this Swedish method, which everything is circular. So let's try one case with the Swedish method. Okay, assuming I have a failure envelope like this. Okay, why I put it like this? Because everything is on scale. If I put it like this, everything could be actually calculated, right? So first of all, the dead weight of this failure mass is what? Is a quarter of the circle minus this triangle will be the area of this funny moon-shaped sort of things, and then just times gamma, you get the weight. You get the weight of this, I don't know how to call it, moon or whatever, right? And then this theta will be simple because actually it's 90 degree, right? And of course, we use trigonometries to calculate this theta. It's 2 pi divided by 4, 90 degree. And then plug everything back into that Swedish formula, you got 4.35. Of course, you see, it's very high, right? What does it imply? This failure envelope is not controlling, right? It's a very safe potential envelope, failure slip plane, which means probably you have other failure mechanisms, you have other planes, which is more critical for this 45-degree slopes. Okay, and actually it's correct because remember we say that this is the case that you have a very deep saturated clay. The FOS is actually 1.1 only, right? Same situation, but if we use the Swedish method, of course, I didn't try many failure envelope. I got 4 point something, right? Really out of order. That means you have to try many, many more, right? In order to turn it into a smaller number. All right. Okay. Good. So let's take a maybe 5 minutes break, and then we talk about this effective stress approach. Okay. And then we could leave earlier today. Let's continue. So we have finished the undrained approach or total stress approach. Let's move to a slightly more complicated effective stress approach. Why is more complicated? Because in our undrained approach or total stress approach, we don't need to worry about Porter pressures, right? Because we mentioned that you don't care Porter pressures because you find u equals 0, you cancel out the second term. So I don't care Porter pressures, right? You used even total stress really doesn't matter because the whole thing will be the strength will be determined by undrained shear strength SU. Okay. Effective stress will be different because now we go back to use C dash and phi dash, which means you need to know the effective stress. And in order to know the effective stress, you need to know the total stress and Porter pressures. That's where the complications come. I slow down a little bit because the math will make you a little bit maybe I don't know how to say, get a feeling that is complicated. Okay, first of all, the symbols that I'm going to use. What you need to remember is R and S. R is the resistance, available resistance. Okay, so that's the shear strength. Be careful of the wording that I use here. It makes you or it slightly complicates the issue, but I still want to make use of these terminologies because some textbooks like to use these terminologies. Available shear resistance is something easy to be understood. Shear strength, right? That's the available resistance, shear strength. As I call the mobilized shear strength. This is a little bit complicated. Okay, and is actually the how to say is actually the stresses. It's actually the stresses come from equilibrium. I will use example to illustrate. Okay, so if your resistance R equals to your shear stress, FOS equals to 1, limit equilibrium. Okay, at equilibrium, marginally safe, FOS equal to 1. So everything starts from first principle, free body. And why we have a free body like this? Because we start with a simple problem. Even though we're talking about slope problems, but I want to use a vertical cut to start our conversations because of geometrical wise, it's easier to be understood. Let's say I have a vertical cut, okay? Forget about why it could stand like that, okay? Forget about that. Assuming that the C is very high, it could stand like that. So the height of that vertical cut is H. Assume that instead of having a circular failure plane, I have a straight line. Okay, simply because I want to make life simple. Instead of make a curved one, I make a straight line. So I have a potential failure plane, the red one. Just like what? Just like here. I have a potential failure plane. But in this case, this is circular or non-circular, it really doesn't matter, okay? Round or whatever. But here it's just a straight line. Okay, and this straight line, even a straight line is still in this material, so the strength is still described by C dash and phi dash. Okay, of course, I make it a little bit complicated, like I call it joint strength, but well, it's not really a joint, just some failure plane. And trigonometry, based on trigonometries, if this is beta, this is also beta, and this is H times cotangent beta, okay? Just the length, okay? Nothing fancy. Now, I have a triangle here, which I want to do the force equilibrium. So I cut this free body out. It's subject to dead weight W, which is the volume, okay, of these triangular wedges times the gamma. And we're talking about 1 meter into the paper. So, well, everything is per meter run. This wedge will have reaction at this plane, right? Because you have your normal stress, you have your shear stress. Okay? This S is not shear strength, it is shear stress. Okay? Equilibrium, just the equilibrium. Okay? Once I have something like this, I could quickly write down my force equilibrium equations, because based on horizontal force equilibrium, vertical force equilibrium, I could write something like this. Okay. Of course, in this case, I'm not actually doing horizontal and vertical equilibrium. Instead, I'm doing something like this because it will be easier to do. Instead of W, I will have this component. Instead of this W, I will have this component, right? And this component is balanced by S, and this component is W sine beta, is this component. And the normal component here is W cosine beta. It will be balanced by this N. So I'm doing equilibrium of this normal directions and parallel directions. Okay. Next. This is from equilibrium. Let's talk about failure. Let's talk about strength. If you go back to our shear strength discussions, I have my tau F equals to C tangent sigma tangent phi, right? Assume this is dry, so really doesn't matter whether it's total or effective, just sigma, okay? And I want to turn this stress to force. So I will consider the length and 1 meter into the paper. So my shear strength will becomes what we call the resistance, which is force per meter run. And my C, which is the cohesions along this plane, will have to times L. L is the length, and 1, because it's 1 meter into the paper. Okay, this is the contact surface. And my sigma will becomes N. N is the force per meter run, and then tangent phi will be just copy the same thing. So it goes to this one. And because of force equilibrium that we obtained previously, we just substitute our N with W something. So it just makes basic substitutions. Okay, and I've denoted here L is simply the length of this surface, and N is simply the reaction force times a sigma times the length times 1 meter into the paper. That's the reaction force. Okay, so up to this point, it's still just pure mathematics, equilibrium. I want to start something simple, considering that it's at limit marginally safe conditions. FOS equal 1. If FOS equals 1, your resistance and your strength will be the same. Sorry, your resistance and your shear stress will be the same. Okay, so we put them equal, and W is simply by trigonometry is the area of this triangle times the gamma, and then you have all these trigonometry things. We will be able to derive this formula. Okay. I skip lots of deviations here, derive here, because it would take a partial differential equations to do it. But this is not important. The important thing is look at this so-called H critical. H critical means this is the maximum height that your material could stand given this C and friction angle and beta. So your critical height will be a function of the strength of the material. That makes sense. It depends on the density of the material. Also makes sense because density will affect the weight of the materials. And the locations, that means the angle of these weak planes. Okay. So this simply gives you a taste of what happened. Okay, we start from equilibrium and then we work on our math to derive the so-called critical envelope. Let's move to something a little bit more difficult, but the same tricks. The only different things here, instead of having a vertical cut, I have an inclined surface with angle I. So the only difference is now your weight of the wedge will be different, right? Because you need a more complicated formula to determine the weight of this wedge. And it's actually not too complicated because you are comparing a bigger triangle and a smaller triangle. And this funny shaped wedge is simply the difference between these two triangles. So you have this formula. Okay. And the rest will be just the same. By doing that, you will find a similar critical sort of height, which is also a function of the material properties and the inclinations. Okay. You don't need to worry too much about the math, how we derive. You see, I skipped this one because this is not the important part. The important part here is that I want you to understand that everything actually starts from basic principles, force equilibrium. Okay, it could be a simple vertical cut, or it could be a funny shaped sort of sloping ground. And you see that when we move from a vertical cut to this sloping ground, it looks more like a slope problems, right? And then the next probably people will do would be, instead of having a linear Phelan envelope, they make a curve. So the same thing, right? Just the same thing. Okay. Right. Okay. What if it becomes more complicated? In previous cases, no matter how the slope looks like, there is no additional driving force. We only got the self-weight of the materials. They even know pore water pressures. What if we make it a little bit more complicated? What if I have a crack? And the crack, remember our undrained case, total stress case, the crack will be filled with water, and then water will have additional pressures pushing the entire block to move laterally. This is the first point. Second, what if I have earthquake? Okay, and this earthquake load would impose a lateral inertial force. So the whole thing will just like move sideways because of that initial force, right? Third, what if we have pore water in this case? We have groundwater, and this groundwater will have some uplift pressures acting on it. right? Or if you got a water table, here, let's say I use blue, it looks like more water. So if I have a water table here, so this failure plane will have water pressures, right? So what I have discussed is try to add more factors which affect the stability of the of these slopes. I basically skip much of the deviations, but you see that I add 3 more things to the free body. Originally, I don't have seismic. I don't have pressure from the crack. I don't have water pressures from bottom. Now I include them all. Okay, first of all, this key will be easy to understand because you got a crack and then you fill with water, so you have these water pressures, okay, acting on this wedge. Second, earthquake. This is a rather simple approach to address earthquake loading because we know earthquake loading is something related to the inertia. Inertia is something related to the weight of the body. So what we're trying to do is to add a horizontal load because it's shaking. We add a horizontal load, and the horizontal load will be described by a fraction of the unit weight. So it's proportional to the unit weight. You may argue, why it point that way? We are talking about seismic loading. It shake in both directions, right? Why I only consider something like that? Why I don't consider the arrow pointing in the opposite direction? Why? Any reasons? It won't be critical, right? Because this is the most critical thing. It's trying to drive your mass moving away. So this is critical. So we consider this case, right? Definitely, you're correct that there will be a case that this arrow pointing in these directions because it's biaxial, sort of bidirectional shaking. All right. And the last one will be something very familiar to us. We got a pore pressure. So the total stress will be decomposed into effective stress and pore pressures. What does it imply? So what? So what? What does it imply? If you go back to this one, sorry, it's a bit messy. So take a look. In the dry case, I replace my sigma with n, right? Because it's dry, I don't have any pore water pressure. But if this not a dry case, I should not use n. I should use what? N dash effective stress. Okay, we should use effective stress. And effective stress, how do we know effective stress? I need to know pore pressures. Okay, so now every puzzle has been bring together to form this free body diagram. And same tracks. Now we have all sorts of arrows pointing in different directions. What we need to do is to resolve the components. So probably we could resolve it like parallel to the failure plane and perpendicular to the failure plane. Or you want to do, well, horizontal, vertical, depends on which one you consider more convenient or easy to do. I normally do like this and that, parallel to a failure plane and normal to a failure plane. Okay, so this is what we have, the equilibrium. So by having equilibrium parallel to the plane, where's my pointer. Okay. I got something like this. By considering normal to the failure plane, I got something like this. And Mohr-Coulomb failure criteria, just copy the whole thing, but replace it with n dash because we got Porter pressures. And everything comes simply from force equilibrium. All right. And in this case, once we put everything back and do a little bit mathematical sort of procedures, deviations, you will get a FOS equations like this. Again, take a look whether it makes sense or not. Let's take a look. We got 3 additional terms, Q, KH, and pore pressures. Let's take a look whether it makes sense or not. K appears on the numerator and denominator. Both, right? Okay, so let's take a look. Minus something, it reduce, increase the denominator. Does it make sense? Yes, right? It brings your FOS further downward. So by same token, okay, Q, same thing. U, same thing, right? You reduce your denominator. You reduce your numerator, okay? So that FOS, at least by looking at the plus minus, by looking at the symbols, it looks okay, right? All right. I don't think I will ask you to derive this one during exam, so don't worry. Don't worry. Okay. You know the concept will be good enough. Okay, let's finish this last slides, okay, before we finish today's lectures. This is something that actually puzzled me when I was an undergraduate student. I always consider seepage water pressures not easy to be understood. Let's take a look what happened actually, what puzzles me. Skip the figures here because I think I have a better way to illustrate the concept. Have you got a chance to visualize a physical model? Let me see, with something like this. When you learn seepage, I don't know what in what's in PolyU. Have you got a chance to read a 1G model, a physical model that shows a dam with high water on one side and low water on the other side? You got a chance to see something like that? And then your TA and professor will say, oh, you got a seepage running through, right? Because if you, I shouldn't use blue because I want to use blue to represent the drainage line, but let's use green. So the professor will say, oh, let's say this is a, let me think how to do it. Okay. This is a, we have seepage flowing. We got seepage, something like this. And they put some dyes here, ink, and then you could trace along. Have you done that? No. Oh my goodness. That's actually quite fun because we put dyes into ink into the physical model, and then the dye or the ink will flow like the water, right? The water will bring it to flow, so we can actually see those float lines. Okay. And if you got a chance to do that, maybe, well, of course, I know you don't. And in a physical box, this is transparent. We attach tubes here, and we attach tubes, and then we see that the tubes will be filled with water. Okay, and this water will be used to demonstrate the water pressures at that particular point. And you will find that the height in this, actually is piezometer, the height of water in this piezometer is lower than the water level at the same locations. You know what I'm talking about? Okay, let's say here. All right, go back to these figures. If you get the pipes here and then connect to the water inside the soil, and if you got the pipes here, the water inside this pipe will fill up, all the way up to this level, but not to this level. So it will fill all the way up to HP, but not H. Why? Because HP is the real water pressure at that point. It's not H. H is simply the height of water that you see at that particular sections, but not the pore pressures. Let me see. I hope next time I could dig out some YouTube video showing you what happens. That actually helps to understand a lot of things. Even when you practice as an engineer, you don't need to worry too much about standpipe and piezometer. It explains a lot of things. So the key message here is that the pore pressure at this point inside the soil, at this point, is not simply the height of water that you see. The pressure is actually smaller than that because water is flowing. That's why we have the so-called flowlet. I think you still remember the so-called flow line and equipotential line. Do you? You still recall these two terms, right? Flow line, equipotential line. And flow line somehow denotes the directions of water flow. Equipotential line is simply the another set of virtual line that perpendicular to this flow line. What's special about this equipotential line is every single point on this will have the same potential, water pressure. That's why we call it equipotential line. And by doing, maybe I skip this one. I use a YouTube video to explain it. It will be easier for you guys to understand. The key message here is that when we do slope W analysis, okay, we want to evaluate the pore pressure at certain points. Normally speaking, people will simply measure the height from this point all the way to the top of the water surface. And you should know that this is incorrect. This is not the pressure. So if you take this as the water pressures, it's only an approximate one. The real water pressure is you have to draw the flow net, which is smaller one. Even in slope W, they make these approximations. In slope W, they use this. Okay. And the bad thing is that some engineers will think that, okay, slope W use this, and they think this is the definition. This is not the definitions. This is simply an approximation that slope W use, because it would be much easier for the program to do the calculations. Okay, and the good thing is, let's compare these two. This is accurate. This is approximate. By using the approximate method, your pore pressure will be higher. That means it's on safe side. So it's okay, right? All right. Okay. So let's stop here. I promise to take out some interesting videos so that you have a better understanding what I'm talking about. But here, the key is, well, we do approximations, but it's still on the safe side. All right. So let's stop here today.